Hello, class. So we are now on section 2.5, okay, which is about transformations of functions, okay, which sounds fancy, but really we're just going to be graphing, okay? So if you've taken algebra in high school or something like that, this was probably a huge part of it. So basically how we're going to graph here is we're going to memorize some original functions. Okay, we're going to memorize some base functions. I remember my calc teacher in high school called them the seven mother functions. So if that entertains you, then feel free to steal it. Okay, but we're going to start off with one that we all know. Okay, f of x equals x, which we know is this line, right? Y-intercept 0, slope 1. Okay. It's called the identity function because when you plug stuff in, nothing happens, right? If I plug in 2, it's 2. If I plug in 4, it's 4. If I plug in -1, it's -1, okay? So that's the identity function. And I'm also going to introduce to you guys today on the internet this website called Desmos, okay? It's very nice. It helps you graph. So here if I type x, ta-da, it's the identity function, and you can like zoom in and you can zoom out, and then if you click on it, you can like check points. Okay, that's 2. You can drag. Okay, so it's very cool. I like Desmos. Okay, encourage you guys to use it for all of your graphing purposes. Here f of x equals x squared. This is another one you should know because I talked about it a couple of sections ago. This one is a parabola. Okay, which we remember is like the U-shaped thing, right? So it looks like this. All right, and if we want to, go on Desmos and just type a caret and a 2, ta-da! It's a parabola, okay? And we see, right, we can check. Here's 1, 1. Here is 2, 4. Right? So a parabola is doing the squares, okay? And then the other one you should know when I talked about x squared, I also talked about x cubed, right? And it looks like this shape. All right. It's kind of like an n, I like to think. I don't know. So here's x cubed, right? You can zoom out and we see it's like this n thing. Okay. Too big. All right. Also, I talked about in that same section the square root function, which, right, we remember starts at 0, 0 and then just kind of goes off, which Desmos is smart. So first of all, how you type in square roots into computers mostly is you're going to go SQRT, and look, it just automatically works, okay? And then I'm going to put X. And we see the graph looks like what I said it looks like, okay? But we also see that the computer is smart, and if I keep trying to go left, it just stops, right? It knows that negative numbers are not in the domain, okay? So, right, this is the first and probably only function with a domain that isn't negative infinity to infinity, right? Remember, this one has domain 0 to infinity, okay? And then there's this one, which, if I'm being honest, this is probably the least important one of the 7 functions. It's the cube root, which looks like this. That's pretty bad drawing. It looks like this. That's a little better. It looks like the cube function sideways. Okay, and that's not an accident. But how I would do that is I would remember that square roots are just fraction exponents. So really, this is a cube root. Okay, and we see it looks like what I said. It's like this kind of like stretched out S thing. Okay, but notice, right, negative numbers are fine. Right, here's -1 and -1, right? Because the cube root of -1 is -1. Just like if I go over here, the cube root of 8 is negative 2. All right, so remember that negative numbers are fine for odd roots, okay? And then also we have the reciprocal function, okay, which if you remember I said looks like this, kind of like half a star, okay? And the reciprocal function is a little weird. One, because remember, well, first of all, its domain is not 0, right? You can't plug 0 into it. But also it has these things, which we'll talk about later on, because this reciprocal functions have their own entire section. But it has these lines that we call asymptotes. Okay, and this one has two. It has a horizontal asymptote, which is this flat one here, and it has a vertical asymptote. And really what an asymptote is just a line, right? A straight line, where the function likes to get closer and closer and closer to, okay? So if I put the reciprocal function here in Desmos, we see. Let me also put the asymptotes. So here I have the y equals 0, the horizontal asymptote. And if you see, right, if I keep going to the right, the red line keeps getting closer and closer and closer to the green line. And this always happens. This will forever happen. It will always get closer and closer. Can I get the red line? Yeah. Closer and closer and closer and closer. All right, but never actually touch. And same thing with the vertical asymptote, right? If I keep going to the left, right, we see that I'm getting closer and closer and closer, like forever. So traveling up, we see getting closer, 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 until basically they look like they're touching, but they're not actually touching, right? All right, so those are asymptotes. That's special about the reciprocal function. And then the last function I need you to know is the absolute value function. Okay. I don't know why I underlined it. Okay. Which that one is a v. Okay. Which I want to make a big deal. All right, it is pointy. All right. It has a corner. All right, because we have another function that looks kind of similar, right? This one, right? This one is smooth. Okay, it's a U-shaped. This one is V-shaped. Okay, and then let me just like graph both of them to make it a little obvious. What if I? Oh, cool. Okay, so here, absolute value x, V-shaped, very pointy. Okay, and then let me get the x squared back up here. U-shaped, not pointy, curved. Okay, curved. And we see that they're different, right? They're not like exactly the same. In fact, they're only the same at 1, right? And -1. That's the only parts where they're the same. The U goes a little more steep. The V kind of looks the same. Okay. So yeah, difference. All right. These are the 7 functions that you hopefully memorize. And then we can use them to graph. Okay. So technically, right, this thing, this ID function, and lines, like straight lines, you technically already know how to graph these, right? Y equals mx plus b, slope, intercept, right? So, right, if we look at this, that's the intercept. So 1, 2, and ta-da, straight line. But how we should think about it now is we have the original function, y equals x, and really what I did is I just went up 2. Okay, so I went the original, and I went up 1, and then up 2, and ta-da, there it is. Okay, sort of. So that's what transformations are. It's like, well, I memorized these 7 things, and then let me be able to like move them around and do stuff with them. Okay, so I'm going to introduce the first transformation we should know, and this is vertical shifts. Okay, so how do I move a function up and down? Which I just showed you, kind of the example. Okay, so there are two rules. All right, y equals f of x plus c and minus c. All right, and kind of what I think everyone would kind of guess is this shifts up c units, and this one shifts down c units. Okay, so if I have a function, right, let's go with x squared. Okay, so the original looks like this. If I were to just put a plus 3, that means I want to go up 1, 2, 3, and then I just kind of copy the function. Okay, so up 3. And then if I had instead like a minus 2, that means I should just go down 2 and then copy the function. Okay, so pretty self-explanatory. I hope we get it. So here I have the square root function, and let me put plus c, and let me get the original on there. No, there we go. So the green is the original, and so here I have plus 1, and look, I went up 1, and then I can just keep going up and down. Okay, up, down. Okay, so if I have a minus 2.2, I went down 2.2 units. Okay. All right, so that's vertical shifts, not complicated, I hope. All right, the next obvious thing I need to show you is how do we do horizontal shifts, so side to side. Okay, so horizontal shifts are when you kind of add a number or subtract, but it's on the inside of the function. So here, if you notice, with the vertical shifts, I'm kind of just adding a number or subtracting it off to the side. Like I could just put like plus 3 here, okay? With horizontal shifts, the number's inside. So that'll be more obvious when I show you examples. But also, it's a little opposite. Okay, so if you see the minus sign, that actually means go right, C units. Okay, and the plus sign means go left, C units. Okay, so I always think about horizontal shifts as maybe being a little backwards. Okay, but let's do an example. So I'm going to have the cubic function and the original. Okay, and so if I have f of x equals x minus 2 cubed, so notice the minus 2 is like inside the cubed. This means go right 2 units. Okay, so right 2. And if I have f of x equals x plus 5, that means 1, 2, 3, 4, 5. That means go left. Okay, that's a little too steep. Left 5 units. So left 5, right 2. Okay. And again, I can show you this. So let's get an x cubed. Then let's do x plus c inside of a cube. Ta-da! And we see when it's plus 1, I went left 1. And then I can keep going left. And I can keep going right. Left, right, right, left. negative 3. I went to the right, 3. Okay? So yeah, that's horizontal shifts, okay, left, right. And now you can combine them, right? So the next question would be like, how do I shift diagonally? And the real answer is we kind of don't, okay? The real answer is we just combine left and right. So here I'm going to have an x squared plus 2 minus 1. This part means I'm going to go left 2, but this part means I'm going to go down 1, okay? So if I were to graph this, I would start with the original, okay? Then do one of these, so I'm going to just go down 1, okay? This is x squared minus 1. And then finish it off with x plus 2 minus 1. So now this is my function, and I'm going to go that one 2 to the left. And ta-da! Okay? And the domain here is negative 2 to infinity. Okay? So yes, this is how you would do it in like steps. And it doesn't matter the order for shifting. I could have done this one first and then the minus 1. That probably would look a little more normal, actually, but whatever. Okay? So let's do this example with the 1 over x minus 2 plus 1. Okay, so here I have the reciprocal function, which is this. Okay, but remember I said that really what I do is I move around the asymptotes. So this purple thing is what I'm actually going to move to the right 2 and up 1. So, okay, so I'm going to go to the right 2. Okay, and then I could just, like, if I wanted to, you know, fill in the actual graph, and then up 1. So right 2, right, I'm here, and now I'm going to go up 1, and then I fill in the graph. Okay, and so this is how I would graph the reciprocal function. Is really I'm moving around the purple cross, and then the actual graph just kind of follows along. Okay. All right, and then I can show you that with Desmos. Okay, so let's go with 1 divided by x plus c. This is going to be a little awkward. So here I'm moving it diagonally. But if I look at x equals c, is that what I need? Y equals c. Nope, it's definitely broken. It works at 0, 0. And then it super doesn't work. Okay. What if I wait? Ta-da! Okay, there we go. So if we see, as I move C around, really like the green lines are just following the cross. Okay, they just follow it along. So I'm really moving the cross around because that's easy to move, right? This curved thing is a little hard to deal with. Okay? Alrighty then. So now that we can move stuff, all right, we have to do another very important one. And this one is reflecting. So reflecting graphs. So again, there's 2 rules. Really number 1's the most important, okay? It's if you have a minus sign, you reflect, okay, or it's a reflection across the x-axis, okay? But if you have a minus sign on the inside, okay, it's a reflection across the y-axis. Okay, so here I'm going to show you. I'm going to use the square root function as my example. So there's square root of x. If I put a minus sign in front, right, I just said that's a reflection across the x-axis. So what you could do is you could think of the axis as like a skewer and the math function as like rotisserie chicken, and you can kind of just spin it, okay, across the x-axis. So what happens if you spin it is, right, you would end up with this thing, okay? Or it's reflected, right? Like if you look at the original, it's this. So like, right, you spun it and it ended up there, okay? All right. Yeah, this is the reflection across the x-axis. Now, if you have negative x, right, that's on the inside, that reflects it across the y-axis. Okay, so that would look like this. Okay, and again, we see, right, like if I draw the original, right, it looks like I just like spun it this direction. Okay. But yeah, this is a reflection across the y-axis. Okay. And so that's important. Okay. But we see here's some special stuff. All right. So if I were to do the same thing with x squared, right? I have x squared. Well, I can do the x-axis reflection, right? Negative x squared will look like this. Okay. But if I try and do the y-axis reflection, maybe I should color code it. This is blue, this is red. What happens is that this is red, and this is blue, but nothing actually happens, right? Like it's the same graph, right? I spun it, and it's the same. And that's because, remember, when you have a negative in a squared, the negative just goes away. So you actually don't do anything. It kind of just disappears, okay? All right. So now that I taught you reflecting and vertical and horizontal shifts, that's really all you need to do for the test, okay? Because I'll just ask you to graph things like this. So like negative x plus 1 cubed minus 2, okay? I'll just combine all three and ask you to like graph it step by step, okay? So the minus sign means flip. The plus 2 on the plus 1 on the inside means go left. Go left 1. And the minus 2 means go down 2, right? So we can have the original. Then, okay, so this is like professional advice because it gets a little complicated. I'm going to advise you to always do the flip first, okay? Or the reflection. All right, so if you do the reflection, you get this, right? This is negative x cubed, okay? And then do your translations. So then I'm gonna go to the left one. So 1 over left. And then I'm gonna go down 2. So down 2. And ta-da, there is my answer, okay? All right, so yeah, just stuff like this, not that hard, okay? And I don't know, let me just slap that in Desmos, just a proof of concept. So here I'm gonna have negative x minus 1 cubed plus 2. that is not what I actually wanted to do though. Plus 1 minus 2. I had the opposite sign. Plus 1 minus 2. Ta-da, there we go. And we see, right, this is the point negative 1, 2. And it's flipped, right? So there you go. All right, now I have to introduce something that like no one actually cares about because at this point you would actually just smash it into a calculator. All right, but this is stretching and shrinking. Okay. So stretching and shrinking is what happens when you multiply by numbers. Okay, so if I multiply a number on the outside and the number is bigger than 1, okay, that is a vertical stretch by C units. Okay. And if the number is a fraction, like less than 1 but bigger than 0, okay, it's a vertical shrink by C units. Okay. So what does this look like? Here's an example. F of x equals 2x squared. Oh, okay. So here's the original. Now I'm going to multiply by 3. Okay, that will do a vertical stretch. So literally just it just makes it skinnier. Okay. And if I were to do f of x and then I multiply a fraction, so like 1/4, that will just make it less skinnier. Okay. So yeah, this is what that does. And let's look at it on Desmos. So I'm gonna do it with what haven't I used? Let's do absolute value function. Okay, so you see that's the original. If I can I do a C? Yeah. So if I multiply by big numbers, you see that I'm stretching it, right? It's getting skinnier and skinnier and skinnier. Okay. But if you see, if I start multiplying by fractions, right, it gets fatter and fatter and fatter until 0, in which case nothing happens. And then if you go negative, then right, you're reflecting because the minus sign is a reflection. So then you have to combine the reflection and the shrink. Okay. So yes, this is vertical stretching, shrinking. The reason we don't really like this though is because it's kind of inaccurate. Like how much do you stretch? How do you know to stretch by C units? The only way to like accurately stretch by that much is if you just like plug in a bunch of numbers, which we're trying to avoid plugging in a bunch of numbers. So not as important, okay? Now, I have to introduce the concept of even and odd, which I already kind of have laid the foundation to, all right? So even and odd. So by definition, all right, the fancy math way to do even and odd is a function, okay, is even if when you plug in negative x, nothing happens, okay, or the negative disappears. This also will look obvious though, because all even functions are y-axis symmetric, okay? So that can probably, right, if we look up here, we're like, oh yeah, x squared, that's totally even because it is y-axis symmetric, okay? And if we remember up here, here's kind of my explanation, right? If you reflect it across the y-axis, really nothing happens, right? It looks the same. So that's even, okay? Next is odd. So the fancy math way to do odd is if you plug in a negative, you can tear it out, okay? Or the negative can come outside, okay? And all of these functions will have origin symmetry, okay? So we can look at this though, okay? Um, just kind of remember, right? I told you that all of these will have the same shape, right? X to the squared, x to the power 4, 6, 8, right? And that's true because they're all even. Okay, same thing with odd. 2n plus 1, right? Basically, because if you try and plug in a negative, okay, so like let me whip out the professional mathematician hat. When you try and plug in negative x, what you can do is this, right? This is negative x times negative x to the 2n. But we know 2n is even. So negative x times x to the 2n, which is negative x to the 2n plus 1. And we see that the minus sign went from the inside to the outside. Okay, and that's what it means to be odd. Okay, so all of the cubes, the fifth powers, the seventh power is odd. So if it has an even power, it's even, and if it has an odd power, it's odd, right? It's like mathematicians name these things for a reason, right? They're like related. Some other functions though, this function, right? Absolute value of x, when I plug in a negative, nothing happens, right? Because that's how absolute, so it's also even. And right, if you look at the graph, it's a V, which is also symmetric, right, around the y-axis. So it makes sense that this is even, okay? So then, the kind of questions you guys could get on exams, though, will not be like that simple, okay? There'll be something maybe like this, okay? Um, is this, what is this? Is this even? Odd? Neither? Okay? And so you'd have to check, right? You would plug in the negative x cubed minus, well, okay, plus 5 minus x, right? The negative would come outside of both of them. You get that. And that's equal to negative f of x, okay? Which that's a little too fancy. What I would actually advise you to do is figure this thing out. Okay, negative x cubed minus plus 5x equals negative x cubed minus 5x, okay? And then like, look, they're the same, ta-da! It's odd, okay? So yeah, you need to like actually be able to plug in and show if a function is even or odd, okay? If you have its graph, then you should just be able to stare at it and tell me if it's even or odd. But let's do some maybe more examples, okay? Well, actually, let me since I'm talking about even and odd, before I get too distracted, right? I told you this, right? X cubed, right? This has origin symmetry. That means that if you flip it, if you like rotisserie chicken it across this purple line, it will look the same. Which this might require, ta-da, sort of, kind of, okay. But yes, back to math. Okay, so let's do some last couple examples of even, odd, neither. Okay, so here I have a function, f of x equals 1 minus 2x squared plus x to the fourth. Okay, is this even, odd, or neither? Well, step one, plug in negative x and see what happens. Fourth. We know that this is even and this is even. So 1 minus 2x squared plus x to the fourth. And then we're like, look, it's the same. So the function is even. Okay. Now, I should tell you to mildly be careful. Because you should check that it's not also odd. Okay. A function cannot be even and odd at the same time. But if I asked you, like, is this thing even, odd, or neither? Okay, that's, if we remember, that's a circle. And that is even and odd at the same time. Okay. But that would be like a really mean trick question. So you probably don't have to worry about that. If it's even, that means it's not odd. And if it's odd, it means it's not even. And if it's none, then that means it's actually none. So here's an example. X squared plus x. Okay. So f of x minus x, you would plug in the negative x. And this one disappears, but this one stays. So we're here. So we're not the same. So you know you're not even. Okay, so then you check, is this odd? Okay, so you're gonna do this one. And you're like, okay, that's this. And I'm gonna distribute the minus sign. And you look at these and you're like, that's also not the same. So it's not odd. So this one is neither. Okay, it's not even or odd. It's nothing. Okay. And then just like, let me be careful. Last example. This thing, x cubed plus 1. Okay, you might all think this is odd because like you're seeing some patterns, which are correct. Okay, if every power is even, then it's even, and if every power is odd, it's odd. But this one, when you plug in the negative x, you're gonna get this. And then when you check to see if it's odd, right, you're gonna get this, which is not the same. Okay, so this one is not odd, and it's obviously not even. Okay, so this one is also neither. Okay, so the plus 1 here is enough to make this function not even. Okay, not odd. So yeah, just be careful, plug in, double check. All right, but that's it for section 2.5, guys. All right, I will see you guys next section.